The single cubic centimeter of cyclotrimethylenetrinitramine contains enough chemical potential to accelerate heavy steel plates to supersonic speeds within microseconds. This energy is not stored in unstable nuclear bonds, but in the precise geometric tension of a six-membered heterocyclic ring. The molecular backbone consists of an alternating arrangement of 3 carbon and 3 nitrogen atoms. Each nitrogen atom within the ring is bonded to an external nitro group, creating a dense cluster of electronegative oxygen atoms surrounding a nitrogen-rich core. This specific configuration results in a high crystal density of 1.82 grams per cubic centimeter. The proximity of these groups creates significant intramolecular repulsion, priming the system for rapid decomposition. Understanding this energetic density requires looking beyond simple combustion into the physics of instantaneous molecular collapse and gas expansion. The stability of the cyclotrimethylenetrinitramine molecule is dictated by its chair conformation, similar to cyclohexane, yet significantly more strained. Nitrogen atoms in the ring adopt a pyramidal geometry, which deviates from ideal bond angles and increases the internal energy of the system. This geometric strain is a primary factor in the high heat of formation observed in nitramines. Unlike typical hydrocarbons, where carbon-to-carbon bonds provide a stable framework, the nitrogen-to-nitrogen bonds in this molecule are inherently weaker, with a bond dissociation energy significantly lower than the carbon-to-hydrogen or carbon-to-carbon equivalents. This inherent weakness is not a flaw, but a functional requirement for high explosives. The strain acts as a storied energy spring, waiting for a thermal or mechanical shock to overcome the activation energy barrier and initiate a self-sustaining chain reaction.
The transition from a stable solid to a chaotic plasma is governed by the laws of thermodynamics, specifically the rapid increase in entropy and the release of enthalpy. When the molecule decomposes, the primary products are nitrogen gas, water vapor, carbon monoxide, and carbon dioxide. The formation of these small, highly stable gaseous molecules releases a massive amount of heat, approximately 1,100 kilocalories per kilogram. This exothermic process is nearly instantaneous, occurring within a reaction zone only a few micrometers thick. Because the reaction produces many moles of gas from a single mole of solid, the volume expansion ratio is nearly 1,000 to 1. This extreme pressure gradient is what drives the physical destruction of surrounding materials. The energy release is so fast that the surrounding air cannot move out of the way, resulting in a supersonic shockwave. Efficiency in an explosive is determined by its oxygen balance, which measures whether the molecule contains enough internal oxygen to completely oxidize its own carbon and hydrogen atoms. Cyclotrimethylenetrinitramine has an oxygen balance of -21.6%. This means it is slightly oxygen deficient and will produce carbon monoxide and solid carbon soot if detonated in a vacuum. However, in atmospheric conditions, the high temperature of the fireball allows for secondary combustion with ambient oxygen. Despite this slight deficiency, the molecule remains one of the most powerful non-nuclear explosives because its energy density per unit of volume is exceptionally high. Modern formulations often adjust this balance by adding oxidizers, but for high-velocity cutting charges, the pure nitratramine ring provides the necessary pressure pulse without requiring external oxygen sources.
Pure cyclotrimethylenetrinitramine is a sensitive, brittle, crystalline solid that is difficult to handle and nearly impossible to mold. To create composition 4, chemists incorporate a mixture of plasticizers and binders, typically diethylhexyl sebacate and polyisobutylene. These long-chain polymers coat the individual microscopic crystals, acting as a lubricant and a shock absorber. This matrix reduces the sensitivity of the explosive to impact and friction, allowing it to be cut, shaped, and pressed without the risk of accidental initiation. The plasticizer also ensures that the material remains malleable over a wide temperature range, from 40 degrees below zero to 75 degrees Celsius. This material science innovation transforms a dangerous chemical into a reliable tool that can be safely transported and applied to complex structural geometries, while maintaining its full energetic potential. The detonation of Composition 4 is not a fire, but a supersonic shock front. While a typical fire spreads at centimeters per second, the detonation wave in this material travels at 8,040 meters per second. This velocity is determined by the Chapman-Touget state, where the chemical reaction is perfectly synchronized with the shock front. As the shock wave passes through the solid material, it compresses the crystals to nearly twice their normal density, instantly raising the temperature to several thousand degrees. This temperature spike triggers the chemical decomposition of the next layer of molecules, which in turn supports the shockwave. This self-sustaining cycle continues until the entire mass of the explosive is consumed. The resulting peak pressure can exceed 25 gigapascals, enough to shatter high-strength alloy steel instantaneously.
The chemical trigger for the entire explosion is the scission of the nitrogen-to-nitro group bond. Modern laser spectroscopy has revealed that this is the first bond to break during thermal initiation. Once the nitro group is detached, it forms a highly reactive radical that immediately attacks neighboring carbon and hydrogen atoms. This sets off a cascade of radical reactions that tear the hexagonal ring apart in less than a picosecond. The nitrogen atoms from the ring find each other to form triple-bonded nitrogen gas, which is one of the most stable bonds in nature. The transition from the weak nitrogen-to-nitrogen single bond to the extremely strong nitrogen-to-nitrogen triple bond is the primary source of the kinetic energy released during the blast. This fundamental shift in bonding energy is why nitrogen-rich molecules dominate the field of high energetics. Safety in explosive handling is measured by the drop height and friction sensitivity tests. Composition 4 is remarkably insensitive. It can be struck with a hammer or set on fire without detonating. Detonation requires the specific high-pressure pulse of a primary explosive, typically found in a blasting cap. This stability is due to the electronic structure of the nitramine groups, which are less prone to spontaneous decomposition than the nitrate esters found in nitroglycerin or dynamite. The polyisobutylene binder further enhances this safety by absorbing the energy of small impacts and preventing the formation of hotspots within the crystal lattice. This allows for precise engineering of the blast, ensuring that the energy is only released when the user provides the exact required initiation energy through a detonator.
Post-blast analysis provides a chemical fingerprint of the reaction efficiency. In a successful detonation of Composition 4, the primary gaseous residues are non-toxic nitrogen and water vapor, alongside carbon oxides. Because the reaction is so clean and the velocity so high, very little solid residue remains. This is a critical advantage for forensic chemistry and environmental safety. The presence of trace amounts of unreacted cyclotrimethylenetrinitramine can be detected using vapor phase sensors, as the molecule has a measurable, albeit low, vapor pressure. These sensors look for the specific nitrogen dioxide fragments produced by the slow ambient decomposition of the nitro groups. Understanding these decomposition pathways is essential for both the detection of hidden materials and the long-term storage monitoring of energetic stockpiles in various climates around the world. When comparing energetic materials, chemists use the relative effectiveness factor, where trinitrotoluene is assigned a value of 1.0. Composition 4 has a relative effectiveness factor of 1.60, making it 60% more powerful by weight than trinitrotoluene. This is largely due to the higher nitrogen content and the superior crystal density of the nitramine molecule. While other explosives like pentaerythritol tetranitrate offer similar power, they lack the chemical stability and moldability provided by the Composition 4 formulation. The high detonation pressure and velocity make it the standard for cutting through reinforced concrete and armored plating. It represents the pinnacle of 20th century energetic chemistry, balancing extreme power with the safety requirements of modern engineering. As we look to the future, new cage molecules like hexanitro-hexaasa-isowertsatane aim to push these limits even further through increased molecular strength.